For 40 years, something has been hiding in plain sight, not in a classified vault, not buried in a secret archive. It has been written in equations, printed in journals, whispered at conferences, and then quietly stepped around. Not because it was small, not because it was irrelevant, but because it was uncomfortable. You trust rockets, you trust satellites, you trust the clean arcs of trajectories drawn across mission control screens. You assume that when NASA sends something into orbit, every variable has been accounted for. Gravity mapped, forces balanced, predictions precise to the meter. But what if there is a paradox sitting right at the foundation of orbital mechanics? A contradiction so subtle that it doesn't crash missions, but so profound that it forces us to rethink what we mean by motion itself. For decades, spacecraft have behaved exactly as predicted, until they didn't. Tiny deviations, minuscule drifts, anomalies measured in millimeters per second, easy to ignore, easy to blame on thermal radiation, fuel leaks, modeling errors. But behind those corrections lies a deeper question. What does it really mean for something to move through space? To understand why this paradox lingered for 40 years, we have to begin with something simple: inertia. An object in motion stays in motion. That is the first law you ever learned. Straight lines are natural, curves require explanation. If a spacecraft leaves Earth and no force acts on it, it should glide forward forever, perfectly straight, perfectly predictable. But nothing in orbit moves in a straight line. Every satellite curves around Earth. Every probe bends around the sun, planets trace ellipses, moons fall endlessly without ever landing. We explain this with gravity, a force pulling inward, deflecting straight motion into curves, clean, elegant, mathematical. But here is the paradox. If gravity is a force, then a spacecraft in orbit is constantly being accelerated inward. It should feel that force. Its instruments should register it. Its structure should respond to it. Yet astronauts in orbit feel weightless. Satellites register no force acting on them. In free fall, there is no sensation of being pulled. So what exactly is being accelerated? Einstein's answer was radical. Objects in free fall are not being pulled at all. They are following the straightest possible paths through curved spacetime. The curve is not in the path. The curve is in space itself. Mass tells space how to curve. Curved space tells objects how to move. If that is true, then an orbiting spacecraft is not fighting gravity. It is not resisting a pull. It is moving naturally, no force required. And yet mission control still calculates gravitational forces. Engineers still model accelerations. Thrust corrections are measured against Newton's framework. For practical purposes, Newton works. For conceptual clarity, Einstein rules. For 40 years, NASA has used both languages interchangeably, and that is where the paradox lives. Consider the deep space probes launched in the 1970s, Pioneer 10 and Pioneer 11. As they traveled beyond the outer planets, their trajectories were tracked with exquisite precision. Radio signals bounced back to Earth. Doppler shifts were measured down to fractions of a hertz. Everything matched predictions, almost. A tiny persistent acceleration toward the sun appeared in the data, so small it was nearly invisible. Roughly 874 x 10 Nach, or 10 meters per second squared. Insignificant for navigation, immense for interpretation. If space is curved geometry and objects follow natural paths, where did this extra acceleration come from? If gravity is fully described by general relativity, why would a spacecraft drifting in the emptiness between planets feel a faint tug beyond calculation? NASA didn't ignore it out of negligence. They investigated, they debated, they published. Some argued it was heat radiating asymmetrically from the probe. Others suggested modeling errors in solar radiation pressure. Eventually, thermal recoil forces were accepted as the explanation. Case closed, except the paradox remains, because the anomaly forced a deeper question. When we say a spacecraft accelerates, what are we measuring? A force, a curvature, a coordinate artifact? Acceleration in relativity is not as simple as it sounds. In curved space-time, straight paths can look curved depending on your frame of reference. What appears as a force in one description is pure geometry in another. If two models describe the same motion but assign different causes, one a force, the other a curvature, which is real? For 40 years, mission after mission has relied on a hybrid language. Engineers compute gravitational pulls. Physicists speak of geodesics. Navigation teams switch between Newtonian intuition and relativistic correction terms. It works, but conceptually it is unstable. Imagine you are inside a perfectly sealed spacecraft drifting far from any star. no windows, no external reference. You release a small metal ball. It floats beside you. No drift, no acceleration. You are in inertial motion. Now imagine that, without your knowledge, the fabric of space itself begins to curve subtly around you. Not because of a nearby planet, but because of some large-scale cosmological effect. Your path bends. The ball drifts toward one wall. Did a force act, or did space change? This is not science fiction. The expansion of the universe stretches space itself. Galaxies recede not because they are moving through space like bullets, but because the metric defining distance is evolving. So when we track spacecraft over decades, are we measuring motion through space or motion of space itself? The paradox NASA wrestled with was not about faulty rockets, it was about interpretation. When anomalies appear, the instinct is to search for a missing force, a leak, a pressure, a photon recoil. But what if sometimes the discrepancy is not in the force model, but in the geometry model? General relativity predicts subtle effects beyond simple Newtonian gravity. Frame dragging, gravitational time dilation, curvature coupling. NASA has measured many of these directly. Gravity Probe B confirmed frame dragging around Earth. GPS satellites require relativistic time corrections every day. Without relativity, your phone's location would drift kilometers off target within hours. So NASA has never truly ignored the paradox. They have lived inside it. Every time mission planners compute a trajectory, they start with Newton, they correct with Einstein, they adjust with empirical data. The spacecraft flies, the data arrives, the model holds. But underneath this operational success lies a philosophical tension. Is gravity a force or a manifestation of geometry? If it is geometry, then the language of force is an approximation. If it is force, then curvature is metaphor. Both cannot be fundamental. One must be emergent from the other. For 40 years, the paradox has been tolerated because it is productive. Newton is computationally efficient. Einstein is conceptually accurate. The spacecraft does not care which language you use as long as the numbers align, but anomalies, however small, expose cracks. When Pioneer drifted slightly inward, some physicists wondered whether gravity behaves differently at vast distances. Could there be modifications to Newtonian dynamics? Could dark matter not be matter at all, but a misinterpretation of gravity's geometry? Most such ideas fail under scrutiny. Data eventually reconciles. Corrections are made. The anomaly fades into footnotes. Yet the deeper issue persists. Motion is relative to a coordinate system. Curvature depends on the metric chosen. Acceleration can be real or apparent. If you accelerate in a rocket, you feel weight. If you stand on Earth, you feel weight. According to Einstein, these are indistinguishable locally. The equivalence principle erases the line between gravity and acceleration. So when NASA measures a spacecraft's acceleration relative to Earth, what exactly is accelerating? The craft, the coordinate frame, the underlying geometry? You might think this is academic. It is not. Interplanetary navigation depends on modeling gravity fields precisely. Small mismatches compound over billions of kilometers. If our conceptual foundation is slightly misaligned, predictions could drift. The fact that they mostly do not is a triumph of physics, but triumph does not eliminate paradox. Consider another subtlety. In expanding space-time, distant galaxies recede faster than light relative to us, not by moving through space faster than light, but because space between us stretches. No local law is violated, yet our intuition rebels. Similarly, a spacecraft can appear to accelerate relative to one frame while moving inertially in another. NASA's anomaly debates revealed something uncomfortable. Our measurement language is not neutral. It encodes assumptions about space and time. For 40 years, engineers have pragmatically bridged two worldviews: force and geometry, pull and curvature, acceleration and natural motion. And perhaps that is the real lesson. Physics does not owe us a single intuitive picture. Nature allows multiple consistent descriptions. The paradox was never that NASA ignored an effect. It was that our language strains to capture reality without contradiction. When Pioneer's data was reanalyzed, thermal radiation explained most of the drift. Tiny asymmetries in heat emission produced a recoil force. Nothing exotic, nothing revolutionary. Yet the investigation forced physicists to revisit foundational assumptions. It reminded them that even millimeter per second deviations matter. That precision reveals philosophy. We like to think of space as a stage and spacecraft as actors moving across it. But if the stage itself bends, stretches, and curves, then motion is choreography written into geometry. NASA did not ignore the paradox. They navigated through it. And that may be more profound than any anomaly, because every launch, every trajectory correction, every gravity assist maneuver is an experiment in the nature of reality. We send metal into the sky and measure how it falls around invisible wells carved into space-time. We trust equations that blend centuries of thought, Galileo's inertia, Newton's forces, Einstein's curvature. The paradox is not a failure, it is a reminder. When you step on a scale, you feel the floor pushing up. When a satellite orbits Earth, it feels nothing at all. When a probe drifts beyond Pluto, its path whispers secrets about geometry. For 40 years, NASA refined its models not because they were wrong, but because reality is deeper than one description. Gravity is not merely a pull. It is not merely curvature. It is the relationship between matter and the fabric that defines distance and duration. If that sounds abstract, consider this. Without acknowledging space-time curvature, GPS fails. Without Newtonian force calculations, rockets miss their windows. Without empirical humility, anomalies become myths. The paradox persists, not as an unsolved mystery, but as a conceptual tension that keeps physics honest. You cannot move through space without asking what space is. You cannot measure acceleration without defining your frame. You cannot dismiss tiny deviations without confronting the assumptions beneath them. NASA's greatest achievement is not eliminating anomalies, it is learning to interpret them without abandoning rigor. The universe does not promise simplicity, it offers consistency, sometimes in the language of forces, sometimes in the language of geometry. For 40 years, a faint drift in deep space reminded us that even the most trusted equations are tools, not truths carved in stone. And perhaps that is the quiet beauty of the paradox. We build machines to cross the void, and in doing so, we uncover how fragile our intuitions are. We expect straight lines, we find curves, we expect forces, we discover geometry. The spacecraft keeps flying, the data keeps arriving, and the conversation between Newton and Einstein continues, not as a conflict, but as a duet. NASA never ignored the paradox, they used it. Because every anomaly is an invitation, not to panic, not to sensationalize, but to look closer. And in looking closer, we refine not just our trajectories, but our understanding of reality itself. The next time you watch a rocket rise, remember, it is not escaping gravity, it is negotiating with geometry. And somewhere in the quiet math beneath mission control, the paradox still hums, a reminder that space is not empty, motion is not simple, and certainty is always provisional. That is not a flaw, it is science.